Design of concrete structure, reinforced concrete design, short columns. Example number two. Let's do a few more example in short columns and then move on to slender columns. In this example, we do have a short tight column as shown in figure, which has number 8 longitudinal rebars, as you can see here in the figure. We do have 8 of these number 8 longitudinal rebars all around the circle. And we want to calculate the design strength a of our column in a kilopounds. So that's phi times Pn. Also, Fy yield stress for steel is provided to be 40,000 pound per inch squared, and F prime C, which is the design strength of concrete, is 3,500 pound per inch squared. So again, we have a phi times Pn, and we don't have this time of the problem for this problem because as soon as we have a phi which is 0.65 times Pn, we have the design capacity of the column. So we don't need to calculate ultimate load. Pn is also a 80% of P naught, nominal axial force, and P naught is equal to 85% of F prime C times area of concrete plus area of steel longitudinal rebars times a yield stress of steel, which is also provided. So first of all, if we calculate the a entire cross section or gross entire section, that's a quarter of pi times d squared, which is 22, and we can get a ag in inch squared, which is 380.13, and also area of steel is 8 of number 8 rebars, which is the area of number 8 rebar is provided to be 0.79 in the ACI codes. So that's a 0.79 area for number 8 rebars or 0.79 inch squared. And if you do the math, it just gives you area of steel. Then when we just replace A steel and A concrete and A steel in the formula to get the axial capacity of the column. So that's a phi times Pn, which is again 65, which is a resistance reduction coefficient times 80% times 85% in the main formula times F prime C times AC. That's AG minus A steel. This is A steel, which is A equal to A concrete plus A steel times A steel times Fy of steel, which is provided to be 40,000. And if you do the math, it just gives you phi times Pn equal to a 709.74 kilopounds, which is almost, one can say that's 710 kips. Let's attempt the last example for short columns, which is example 3, which is a square cross section with 12 longitudinal rebars all around the cross section. Mhm. So again, in example A3, an 80-inch square tied column. So this is our column. Mhm. With a 12 number 9, with a 12 number 9, mhm, grade 60 rebars. Calculate the design. Again, design axial load is asked is the same like a question example number 2, but with the difference is we are working in a square cross section. So for 60 grade rebars, Fy is 60 times 60,000 pound per inch squared, and F prime C is provided to be 4,000. Mhm. Again, we do not need this part of the problem because as soon as we have phi, which is a resistant reduction factor of 0.65 times a nominal force, axial force, we can get the capacity of axial load of the, so we don't need this part. Mhm. So Pn, nominal P is 80% of P naught, and P naught is 85% F prime CAC plus A steel times Fy. So design axial load capacity is equal to a gain phi times Pn, which is 0.65 times 80, 0.80 times in bracket 85. And if you replace that in the equation, it just gives you 4,000 area of concrete. Mhm. And that's area of concrete. It just gross area minus A steel. So this is 80 times 80 is gross area. 80 squared is the entire minus the rebar. It just gives us the area of concrete. Uh-huh. Then plus a 60,000 times area of steel. And if you do the mass, it gives you mhm, this equation. And at the same time, for a rebar number 12, number 9, the area is 1 inch squared if you look at the table, and 12 of them is 12 inch squared. So AS is 12, and if you replace that by a 12 and do the mass, it just gives you phi times Pn is equal to 926 kilopounds force for design axial capacity of the section. So that's design capacity of the section is almost a 930 kilopounds. Thank you.